This is a circle. We will imagine the circle to be spinning. That dot represents the center of the circle. Let's watch the disk from the side. Now we add a pole through its center. Can you imagine the spin direction? Now it's tilted. Now tilted the other way. Let's add another disk. This disk is smaller. Question: what vector is shown here? Time's up. If you answered outward from the shaft, you are correct. The centrifugal vector is always perpendicular to the axis of rotation. The axis would be the center. See? So what happens when you tilt the disk? Nothing. It still has the same vector. Now let's take a sphere. Does the vector change? That would be a no. The moment of inertia is just greater at the largest radial, as the tangential velocity is greater due to the distance from the axis. So the vector would be outward, straight from the center axis. So if the Earth is tilted and spinning around its axis, any object on the surface will be conserving angular momentum. Don't get too excited, globe believers, as this is not how you think it is. Let me try explain. First, you need to remember, you have to be on the surface to retain this angular momentum. So anything not attached to the surface does not conserve angular momentum. Very simple. So now you're asking, what happens when you do leave the surface? For this we will look at a circle again. Since the vector is outward from the rotation, by leaving the surface you would fly with a linear momentum outward. Let's add Bill to the surface of Earth. Showing the path from the axis, Bill's path when he leaves the surface, notice the linear path. See how he gets higher in altitude from the surface. Jane will stay on the surface as Bill will leave the Earth's surface. Okay, let's act that vector again. Watch carefully. Jane is moving along the surface and Bill, he is seeming to go upwards and away from Jane. I would freak out at this point. Look at that altitude compared to Jane. So based on Jane's reference frame, Bill looks like he's flying up and away. Based on Bill's reference frame, Jane is moving down and away. This tells us that Jane is on the rotating surface and conserving angular momentum, and Bill has left the rotating surface and thus has a linear momentum. Bill no longer has angular momentum. For Jane is in the non-inertial frame and Bill is in the inertial frame. Let's look at it from another view. Let's slow it down a bit. Jane, Bill. Bill has left Earth's surface. Jane is still on Earth's surface. Bill following linear vector, Jane following the angle of rotation. Bill rising in altitude from surface. Bill conserving linear momentum, Jane conserving angular momentum. So because Jane is moving on the curved surface, it seems Bill's linear momentum is curved. So what does all this tell us? You only conserve angular momentum if you're attached to the rotating surface. You follow a linear path once you left the surface. The vector is always linear from the axis. You require a rotating surface to experience these vectors. You have two reference frames as soon as the object has left the non-inertial reference frame. The rotating reference is the non-inertial and the one that's left the surface is the inertial. So this implies that all objects leaving Earth's surface will have an apparent drift as the ground beneath it will move. This would be seen as the Coriolis effect.
I think I've found a way to show an effect that will have you doubting your very own eyes.
Show an effect.
Now, they don't know it yet, but our budding ball players sitting on our specially rigged merry-go-round are about to demonstrate a rather astonishing optical illusion.
Optical illusion.
Here's the game, right? You're going to throw the ball straight. So what's your name? Victor, right? One second comes to you, Spencer, and you think it goes straight ahead, but you think you'll be the one catching it.
Yeah.
Now remember, the ball will be thrown straight across the spinning merry-go-round.
Now remember, the ball will be thrown straight across the spinning merry-go-round.
But where will it end up? Will it be caught by the thrower? Will it be caught by the person opposite? Will it be caught by the person to the thrower's left? Or by the person to the thrower's right?
You got this.
So the answer was D. It was caught by the person on the thrower's right. Our camera angles seem to show the ball bend in the air.
The angles seem to show the ball bend in the air.
So is that a camera effect, or are we seeing what they saw? So let me get this straight. So you threw the ball, it left your hands, and then what?
And then it just got sucked over to him.
In the air?
Yeah, I threw a perfect throw.
What did you see?
Yeah, curved right in it.
Right, so we're all agreeing here the ball curved in midair.
Yeah.
Yes.
Right, so we all agree here the ball curved in midair. Yeah? Yes.
And you didn't cheat this at all?
No, I didn't.
Okay. And do you know why it did that?
No.
Nope.
No idea.
It's called the Coriolis effect. It's called the Coriolis effect. It's called the Coriolis effect. And it's very simple. It's objects in motion appearing to be. It's an optical illusion. Appearing to be. It's an optical illusion.
Appearing to be. It's an optical illusion.
Appearing to be deflected off their intended course. So what's actually happening here is you are throwing this ball. You can only throw a ball in a straight line. Can I clear that up straight away?
Yes.
Even though it appears in your eyes to be bending. So you throw the ball straight. It's still going straight, but the table is moving below you. But the table is moving below you.
But the table is moving below you.
And all of a sudden, look who's in front of that straight moving ball. And it looks like it's bent off to the right because you're still looking at the guy you were intending to throw it to. And that, ladies and gentlemen, is the Coriolis effect.
Great. So we see the Coriolis effect is just optical. But Coriolis force, you say? What if I told you there is no Coriolis force? It's the misinterpreted force called centripetal force. Centripetal force, a net force that acts on an object to keep it moving along a circular path. This net force is inwards to the axis of rotation. The force always acts inwards as the velocity of the object is directed tangent to the circle. The centripetal force acts upon the object moving in a circle at a constant speed.
Said you had two velocity components, right? Number one, we have the water that's shooting out of the spout, which gives it a velocity in this direction. And number two, it's being slung around by rotation, which gives it velocity in this direction. Just like before, let's add those arrows up. And again, the water is still moving in a straight line. Just like before, you can track any particle and follow it, and you'll see that it's moving in a straight line away from the nozzle. The fun thing about this device for me is that it's tricking my brain into thinking that the water is actively curving out in front, but it's not. Your brain tricks itself into thinking the water is turning.
Tangential velocity is greater here than here, aka the surface than in the center. This means the closer you are to the axis, the slower the surface velocity is. Common sense. Ball at the equator would be traveling faster due to the larger radial value. The more north he goes, he will be traveling slower. At the poles, Ball will be the closest to the rotational axis, thus he'll move slower. That means his moment of inertia would be greater at the equator compared to the less moment of inertia at the poles. Now I need to remind you of something. Only on the surface will you be conserving angular momentum, and that vector is outward from the rotational axis. So that would mean you would go up and not north or south. Anything leaving the surface would have a linear path away from Earth in the direction it took off. So if you stood on Earth's surface, it would be seen as an apparent deviation. This includes any object leaving the Earth's surface, including a balloon, because it's not attached. You will have a linear path due to the centrifugal force. And just for the people who claim planes and so forth are not affected by the Coriolis, thoughtco.com. What is Coriolis effect? Well, I'm not going to read everything for you, but I just want to show you. It's an effect known as a Coriolis force. Refers to the apparent deflection of objects such as aeroplanes, wind and missiles. It's an illusion produced by the rotating frame of reference. Without this rotating reference, you wouldn't have the illusion. So it occurs when the object is taking a straight path viewed from the non-fixed frame of reference. Question: can anyone provide evidence of planes, helicopters, balloons and so forth having apparent deviation and flying off into space? Time to be honest with yourself. We do not live on a spinning geoid in a natural violation vacuum. The Earth is a stationary horizontal plane with topography. Thank you for watching. God bless.